Hi. Number 2, Young's double slit experiment. Now, Young's double slit experiment is a famous physics experiment. Just about every physics student will have to learn about it because it's a benchmark experiment. It's beautiful in its simplicity, but it's the complications of its results are profound. So, who's Thomas Young? Well, there he is, 1773 to 1829. There was when he was around, and what he did was a very simple apparatus in that some people put him as using a candle, other people put a hole in the wall or a hole in a curtain, so he has a darkened room basically. Using a hole or a candle gives you a light source that's coherent. That means it's all in phase. All the waves that are coming from the candle or the hole are in phase. He then shone that light onto two separate holes in a card, and then that light shone onto a screen. And he, like many people, would have expected that the light would have formed two bright spots on the screen. However, he observed not two bright spots, but a series of bands and bright and dark spots on the screen. And this is the interference pattern. He was very quick to observe that was the interference pattern. That's exactly the same sort of pattern that you get with sound in terms of loud and soft, or water waves in terms of nodal and antinodal areas in a wave or a ripple tank. And so that's categorical evidence of light being a wave. Now it gets more complicated than that. In the modern world, people wanted to work out exactly how this worked and why light was behaving like a wave, and we now know that light's made up of things called photons, and we'll do that in the next series of videos. But these photons, physicists can now fire single photons, and they act like particles. And what scientists were interested in doing was, well, what if we fired single photons in a Young's double slit experiment? So the photon would have to go through, come to the slits, go through one hole, and we should see bright spots, two bright spots where the photons went through either of the holes. And in various situations they did that, fired single photons, and even when you fired single photons, you got an interference pattern. So the conclusion from that is, of course, that the photons actually went through both slits at the same time and re-emerged, or a single photon went through both slits at the same time, re-emerged, recombined, and interfered with itself, effectively, to produce this interference pattern. How do they know that? Well, if they put a photon counter on the slits, so that you're actually watching which slit the photon went through, you got two bright spots. And so if you took that monitor away, you got the interference pattern. And that's an example of the weird and wonderful world of quantum mechanics, where the observation can determine the outcome, or the mode of observation can determine the outcome. And but we won't delve into that. We need to just look at Young's double slit experiment in terms of the interference pattern. Now you can go to the animations on the OneNote where we looked at sound and water, and there's a light one, and you can have a look at the patterns produced by that and experiment with that. So this is another diagram which is basically showing what he did. There's the first slit, or the candle, or the hole in the glass. That produces a coherent wave, and that coherent wave hits both of these slits at exactly the same time, so you get a crest and a crest. And then you get diffraction happening, and these lines interfere, and you get this dark pattern, and you get a central maximum, which is here. They've actually got it around the wrong way, really, because that point there should be a bright spot, and that should be a dark spot. But I think what they're trying to show is this is photographic paper, and so if this was photographic paper, that would be black once it's developed, because that's what happens with photographic paper. Bit confusing though, isn't it? Here's another one that shows the same thing. This has got it around the right way. Now here they're using a coherent light source. This time it's sunlight from a single slit. Hits the barriers. You get destructive interference. You get there, which is the dark spots, and then you get bright spots, and there's a gradient from the bright to the dark, and the dark spot is, there's only a very small section that's completely dark, and it's a gradation between the two. And so when we say the dark spot, we mean the center of the dark area. And another diagram, again showing it. This one's drawn the wave paths, and so when you're getting destructive interference, you're getting crests and troughs together. When you're getting constructive interference, they're arriving at the same time, and that's why you get the bright dark. Now sometimes you see it also displayed as an intensity curve. We saw that with sound, where we'd have, say, quiet sounds here and dark sounds, quiet sounds here and loud sounds here. And so for light we would have, what's this? This is dark here and bright here, and it goes for. And you can see that the bright and dark spots are evenly spaced as well. Not to be confused with the interference pattern you get from a single slit, which we won't do. And again, another diagram. In this case they're saying monochromatic light. Now what do they mean by monochromatic light? That means it's light of only one wavelength, and something like a laser produces light that's only of one wavelength. And that's something else I forgot to mention. Usually you only use one color of light, so one wavelength of light. If you shone white light through Young's double slit experiment, you get a much more complicated pattern. You can decipher it, and that's what Young managed to do, but it's much easier to see when you're only using one wavelength of light. And we'll demonstrate this in class. We'll get a laser out and put it through some double slits, and we'll see what it looks like. And we should see something like this. This is where a red light laser has been shone through two slits, and you get bright, dark, and evenly spaced. And this other bit of noise around here is just a bit of noise from the edges of the slits probably. So we should be fairly familiar with the geometry of two source interference, where you have a distance between the slits, you have a distance from the slits to the screen, and then you have usually a distance from the central maximum to whatever point you're interested in. And through that we can work out the path difference. So, but however, we would recommend that you use the formula on your information sheet that we use here in Tasmania, and that's the W equals lambda x on D, where W is the fringe spacing in meters, lambda is the wavelength in meters, X represents the slit to screen distance, and D is the slit spacing. So that's a little bit different from what we had in our textbook. And you should now be able to do these questions, but I'm going to go through an example for you just now. Let's just have a look at it. Monochromatic light from a laser, so that's just light of one wavelength, is shone onto a pair of slits. We're given the slit distance. Interference pattern is produced on a screen at the other end of the lab, 3 meters away. It was observed. It says 3 meters from the laser, but it's actually, we'll consider it 3 meters from the slit, because that's what we're interested in. And it was observed that the first order bright fringe was 9 millimeters from the center maximum. Okay, first off, let's draw a diagram, what it looks like. And so we would have our monochromatic light coming in like so. We would have our slits like so, and the distance of this is what, 0.2 millimeters, which if we're careful and we convert that to meters, gives us 0.0002 meters. Then we have our screen. Let's do some different colors. We would have a center maximum there. Okay, and then in this case we've got a first order bright spot. there, and we're told, and so the light's actually going from here to there, and from here to there. Let's change colours again. And we're told that that distance here from here is of course 3 meters, and this distance from there to there is 0.009 meters. Converting everything into our standard units. And there's our diagram. We could also recognize that if we were to calculate the path difference, that would be the path difference there, and because it's the first order bright, that path difference would be what? Would be 1 wavelength. Now, we're actually asked to determine the wavelength, so we don't know that measurement, but that's our diagram. Let's move on. Let's get rid of that. Let's move on to the next section. Whoops. And that is working out the wavelength. So we've got, let's go back to a nice color that we can see easy. Let's go, what do we got? We got W equals lambda x on D. So if we just put the numbers in, there's our 9 millimeters. Wavelength is our unknown. X is 3 meters, and our slip distance is 0.0002. If we rearrange that and solve it, we get 6 times by 10 to the minus 7 meters, and that's good enough an answer. In our textbook, however, they usually give the answer in nanometers, and you might be asked to give nanometers because when we talk about light, nanometers is a convenient unit. Now, a nano is a multiplier where the multiplier is by 10 to the minus 9. Okay, 10 to the minus 9. So if we were to convert this to 10 to the minus 9, it would be 600 times by 10 to the minus 9 meters. And therefore, that would be, our answer would be, in nanometers, 600 nano, because the 10 to the minus 9 is our nano, meters. And that's our wavelength in nanometers. Sometimes throws students out a little bit. Now, determine the distance to the third order dark fringe. So we've got the wavelength. Now the third order dark fringe, let's get rid of that writing when you're ready. Third order dark fringe, if this is our screen again, and there's our max, we would have a bright, let's go up here a little bit, bright, and our dark, let's draw our dark in red. So this would be a dark, so that's our third order dark. Okay, now back to, let's go to green this time. Now in the previous question, or we're actually told that the, where are we? We're told that the fringe distance, because we're actually told the distance to the first order, this is the first order bright, so we should recognize that that distance there is equal to W, which is equal to 0.009 meters. And because these are all evenly spaced, that W is the distance between the next bright fringe. It's also the distance between two dark fringes. So if we go back to, let's go something purple. So what we're interested in is this distance here, and we should recognize that that's going to be 1, 2, so that's W, and this is a half a W, so 2.5 fringe distances, so that's 2.5 times by 0.009 gives us our spacing. What's that going to be? 0. I've done the calculations earlier. There's our distance to the third order dark fringe. Hopefully we followed that. Now determine the thickness of the center maximum. Well, we should also recognize, now I'm using every color I possibly can here, I think. let's go for this one. Now, what's the thickness of the centre maximum? Well, if we have another, we would have another dark just there. And so the thickness of the centre maximum is the distance between the two dark spots, or dark or nodal points, either side of the centre maximum. So we're actually after the distance, that distance there. And we should recognise that that distance there from the dark spot either side of the centre maximum is also equal to W. And so that's going to be 0.09 meters. So if we work like that, and if we're systematic, Young's double slit experiment questions are pretty straightforward. Hopefully you haven't got any questions from that. I'll get rid of that, and then we'll click on this, and the next video we're going to actually look at light interference and just some examples of it. See ya.